All right, I think we can get started. By the way, I've seen some questions about project 1 on Classroom. We'll try to answer that as soon as possible. Tomorrow, next week is midterm week, so I hope that you guys have some time anyway. So yeah, we'll try to address the questions as soon as possible. All right, before we begin the practice session today, as I said, I will try to cover the BatchNorm and some popular CNN architectures. So yeah, we have a lot of ground to cover today, so we'll just get right into it. So the last Tuesday, I was about to talk about how to remove internal distribution shift, but someone asked me if I could explain the internal distribution shift again. So we'll start with distribution shift. So distribution shift is when your model is trained, your CNN or your machine learning model is trained on one type of training data. So the training data which has a specific distribution, data distribution, and you try to deploy it, or you try to evaluate it on a test set which has a different distribution than the training set. So the example here is that, for example, if both MNIST and Cypher10 has the same resolution, 24 by 24. If they it's an assumption. If they have the same resolution, but you've trained your model on MNIST, but you try to train it on Cypher10, then they are vastly different images. MNIST is just digits, but Cypher has airplanes and animals and humans. So your model won't work well, obviously, because what it has learned and what is being tested on are vastly different. So that's what distribution shift is. And machine learning models are usually vulnerable to distribution shift. But there's another thing called internal distribution shift, which is what the first BatchNorm paper tried to address. So I'm not sure if they were the first one to actually recognize the problem, the internal distribution shift, but at least they try to handle it with batch normalization. So what happens is, if you have a multi-layer perceptron or any multi-layer deep learning model, then in this layer's perspective, this layer, the activation of this layer is the input to this layer, right? So because the output of this layer is being propagated to the next layer and the next layer and the next layer. So this layer's input is this layer. So for example, the kth layer's input is the k-1's layer's activation or output, right? And in the same sense, if this layer has learned to adapt to certain distribution of this layer's output and it changes, then it's going to have a hard time adapting to the new distribution. But that's what happens when you update your model parameters. It's because the values of this layer's output changes, or it depends on the weight parameter of this intermediate layer here. There's a weight parameter, so there's like some non-active. So this is k-1's layer. This is k, and for example, there's a FWK. I'm just going to say X. Let's just say H. H k-1 plus B, BK. So this is what happens. So this is what happens between k-1's layer, k-1th layer, and the kth layer. And so that means kth layers, this kth layer's input is this guy, is this guy. And after a parameter update at each iteration, this guy, so this and this changes, and that means k's input changes after each parameter update, after each gradient descent update. So that means the distribution changes in the perspective of k after each iteration. So that's not good. So because each layer has been trained to adapt to a certain distribution from the layer beneath, from the input, which is determined by the layer beneath. And if that changes, then everything is just thrown off. So each layer has to adapt again to the new distribution. So that's not good. So this is exactly what it says here. So each parameter update changes layer k-1's activation, and it forces layer k to adapt to new distribution. So for example, this could be like, so this is k-1, this is k-1 layer's output. For example, let's say that it's an output and it changes after like iteration. Maybe this is iteration 1, this is after iteration 2, this is iteration 3. Like each iteration, the distribution changes, and in layer k's shoes, that is not a good thing. So that's what internal distribution shift is. So in order to remedy that, it's just, I mean, the concept of batch normalization is not that difficult. It's just, let's just, normalize everything. So just like you can normalize the input to the model, I mean the entire model. So you can normalize the entire data set, entire training data set using this, assuming that your training data set is normally distributed, then you can just z-normalize your input like this. And in the same manner, you can normalize the output or the activation of all your layers. Every single layer's output or activation, it can be normalized. So that's what batch normalization is. So yeah, the values over so you, okay, so there's a question. This before I answer the question, so this algorithm here is assuming that you are applying batch normalization in just one place. Like even though there's like a lot of layers, this is just an example. I mean, we're talking about the concept of batch normalization. So let's just say that you are applying batch normalization just between here, just like here we apply batch norm just here. So in that case, what we do is we take the mean of the output. Because what we eventually want to do is x minus mu minus divided by sigma. But this is not actually x. This should be an h because we're dealing with internal distribution shifts. So we need to work with the hidden layers value. But here it's just they just denoted that with an x here. So this should be like an h. It's just a generic notation. So what you need to do in order to do this is you need to know this and this. So that is how you calculate. That is what you calculate here. You calculate the mean, calculate the variance, or maybe or standard deviation, whichever, and then you do the normalization. Remember that this is happening between layers, intermediate, like between two layers, not on the training set. And there's a caveat. So there's one more a bit of a technique applied here, which is scale and shift. This is to relax the how do I say it? Relax the objective. Let's just say that. Yeah. So just trying to force your activation values in all layers to a normalized value to like unit to follow the unit Gaussian distribution like this is a bit of a harsh policy. Like trying to force every single thing to follow a normal distribution is a bit a strict guideline. So instead what BatchNorm does is it allows some room to to grow or to shift around. So that is what this is here. So once you've normalized it, you scale it and you shift it. You scale it and you shift it. So this is a scale factor and this is the shift factor. So that means you even though the spirit of batch normalization is to normalize everything to follow a unit Gaussian distribution, but still it allows some room to wiggle, so that your at least that guarantees some performance. So that's what basically BatchNorm is. And in order to do scale and shift here, in order to do this, you need to actually learn gamma and beta. So this is a learnable parameter. So you just have two more learnable parameters here. In order to do batch normalization, these are like deterministic operations. You just take bunch of batch norm. You just take a batch of data, and then you calculate the mu and calculate the sigma. But what you need to do is, in addition to that, you need two more learnable parameters, which are gamma and beta. This is just like learning a bias term or learning a weight matrix. You just have two more scalar values. All right, bunch of questions. 네, 분포가 달라지면 방금 여태까지 얘기했듯이 분포가 달라지면 각 레이어마다 또다시 새로운 분포에 맞춰서 웨이트를 배워야 되기 때문에 그거를 바꿔주려고, 그거를 맞춰주려고 하는 겁니다. 네. 안 그러면은 열심히, 그러니까 이 어떤 K번째 레이어가 열심히 이제 그 이전에 K-1 레이어의 아웃풋에 맞춰서 열심히 학습을 했는데 그게 스케일 완전히 또 바뀌어버리면은 디스트리뷰션이, 그럼 이제 또 새로 완전히 또 그거에 어댑트하는 시간이 필요한데 그걸 이제 줄여주려고 이제 항상 비슷하게, 그러니까 모든 레이어의 액티베이션 항상 비슷하게 디스트리뷰트 있으면은 훨씬 더 쉽게 접근할 수가 있거든요. 그러니까 조금만 배워도 되잖아요. 이게 물론 이제 로스를 이제 미니마이즈 하려고 당연히 이제 그 변화가 일어나지만 그 변화량이 줄어든다. 그 변화량이 작다면은 각 레이어마다 배워야 되는 양이 줄기 때문에 그게 이제 훨씬 쉬워집니다. BatchNorm이 나쁜 영향. So I'm not sure if BatchNorm can have a bad effect. I think it can have a bad effect if you don't do the scale and shift, but I'm not sure if I think it's generally a helpful thing. Like the magnitude of helpfulness, that depends, but I don't think it hurts at least. All right, I don't have a lot of time, so I will just address the question maybe in class. Okay, so yeah, so what the whole idea is this. So you just want to you want to let you want the activation values of each layer to follow roughly the same distribution. I say roughly because there's a scale and shift factor here, but roughly, like we hope that it'll just follow like maybe around here, 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 or something like this, rather than vastly moving like this. If the activation value of each layer it follows like a similar distribution, then it's going to make the job of layer K easier. Okay, so technically it's not that difficult. So what you need to do in each what you need to do in each layer, and especially in convolution. So because BatchNorm was again proposed in the context of convolution because people were using like multi-layer deep convolutions for classification back in the day, like 2015. So it was proposed to remedy the internal distribution shift in the context of convolution. So we're talking about convolution, so that's why there is a channel here. So per channel mean, so shape is, so we're going to assume that this is, you have a batch of n samples, and in each sample will have a certain dimensionality. So for example, if you are talking about multi-layer perceptron, then you can set your input. So your input could be 784, but your internal dimensionality could be 128, 120, something like this. So that means D equals 128 here. And it says channel, but you can think of this as just hidden feature dimensionality or something like that. Yeah. So per channel, per feature or per column in your internal hidden layer dimensionality, per column or per feature, you take the mean in this direction. So there should be like 1, 2, 3, 4, like 1 to 1. This is H 0. This is H. No, not a good notation. Yeah, this is just this is like 0, 1, 2, all the way to 127. So you take each dimension. Each dimension is mu or mean here. So that's what happens here. And you also do this the same for the variance or the sigma. And then you apply BatchNorm per dimension. So it's called batch normalization because the normalization or calculating the mean and the sigma happens across the batch. So for if your batch consists of maybe 64 samples, then it happens over you collect the value over 64 different samples, and then you calculate the mu and sigma and then apply it on each dimension like this, each dimension. Right. So yeah, so you take the normalization, and then this you will have 128 mu's. So there will be 128 mu's and 128 sigmas, and then you apply it to your n by d matrix, and then your output would be, of course, it's a normalized matrix of shape n by d again. Right. Yeah, the problem is yeah, again, this is the same motivation. If this is a too hard of a constraint or too harsh of a constraint, then you want a bit of a wiggle room. So there's a wiggle room here. You learn a gamma and beta, and as I said, this happens on each dimension of your hidden layer. So there will be gamma and beta for each d. Like there will be 128 gammas and 128 betas. Right. And yep, the problem, I mean, so the whole idea is not that difficult. It's just you just at each mini batch update, you collect the mean and the variance for each hidden layer dimension, and then you normalize it, and then you scale and shift it, and that's how you get the same n by d matrix in each hidden layer. And you just set the gamma and beta as a learnable parameter. And so technically it's not that difficult. When it's training, that's all you need to do. But the problem is in the test time, so not the training time, but on the test time, when you test the test data, you don't necessarily have a mini batch of test samples. For example, maybe you when you deploy your model, maybe you'll just test your model, or you just do the inference, or you use the model one sample at a time, just one test sample at a time. And in that case, you don't have a mini batch. And if you don't have a mini batch, you can't calculate this value because batch normalization depends on the mini batch, right? So in that case, there's a problem. So the problem between the discrepancy of the mu and the sigma between the training time and the test time. So you need to do a bit of a trick, when you want to use batch normalization, when you trained your model using batch normalization and you want to test it on test time. So you just save the mu value as you train your model. So when you train your model, you'll do a bunch of mini batch updates, and at each mini batch update, you will calculate mu's and sigmas, and you just don't throw away after your mini batch update. You keep them around, and then you do a running average over each mini batch update. So for example, if you do mini batch update for like maybe 10,000 times or maybe 100,000 times to train your model, then you just save those values and just do the running average. You add them divided by 2, then add them divided by 2, and add them divided by 2, something like that. Like you just keep a running average, and then you keep the mu's and sigmas around so that you can reuse them when you test your model at test time, right? I mean, these will be around. Like gamma and beta are learnable parameters. So when you've trained your model with batch normalization, then the gammas and betas will be there. It's just that the mu's and sigmas need to be there around so that you can reuse them at test time. So at test time, you still do the same thing. Right. So the original batch normalization was proposed to be slid between a fully connected layer and nonlinear activation. which is kind of weird to me actually, because in my head, a layer consists of fully connected network with the nonlinear activation function. So if you want to do batch normalization, then you probably want to slide it here instead. So there's like FC, and there's like there's nonlinear activation function. Then you slide in the batch norm. So that is how you slide the batch norm between each layer, because there will be another FC after this, then nonlinear layer, and then maybe you can do another batch norm. Yeah, so the originally the paper suggests this architecture, but I mean, when I searched on Google, I read like a GitHub article where it says that the original authors, Sergey Ayev and Christian Szigeti, they actually implemented it in this way, not this, but in this way. So it's still a topic of debate, like which is like more appropriate approach, or which is more effective. But I would say this, to my mind, to me, this seems more natural. This one seems more natural. Yeah. Okay. So yeah, that's this is a summary. So yeah, it makes the deep learning model much easier to train, and that's because it just stabilizes the whole thing, and that means you can have a higher learning rate, which means you can have faster convergence, and yeah, there's a lot of benefit coming from it. Also, I mean, I guess it could act as a regularization, but I'm not sure if this is kind of too big of a factor. Yeah, the only caveat is it behaves differently during training and test time. So this is the only downside of using BatchNorm in my head. All right, so there are different stuff. There were some variations of batch normalization. There was BatchNorm. First, when BatchNorm was proposed, obviously it was proposed in the context of convness. So as I said, BatchNorm on fully connected network is quite easy. You just have an n by d matrix, and then you calculate the mu and sigma over the different samples in the mini batch. So this becomes 1, and the dimensionality is kept around. It is preserved. If you do it for convness, then how it is applied is you calculate the mu and sigma over the entire samples and height and width. So the spatial information is also kind of collapsed here. The only thing that survives is the channel. So you just have the mu's and sigmas per channel, and then you apply BatchNorm. And there's another follow-up work called layer normalization, which doesn't have the discrepancy between the training time and test time. So if BatchNorm calculates the mu and sigma over the mini batch, layer norm calculates the sigma and mu and sigma over the dimensionality, the hidden layer dimensionality. That's the difference. So it doesn't depend on the mini batch, the size of the mini batch, whether it's 32 mini batch size or 64 mini batch size. It doesn't really matter, as long as you just have some hidden dimensionality, then it'll work for you. So layer normalization is another type of normalization which behaves the same. So same behavior in train and test time, and it can be used in recurrent neural networks as well. So you will run into layer normalization when we learn transformer. Actually, transformer uses layer normalization inside. Yeah. There's also something called instance normalization, which is strictly for convness, in my opinion. So you just you don't, when you calculate the mu and sigma, you don't collect information over the n like here. So BatchNorm calculates the mu and sigma based on the samples and the height and width. So there's all ones here, and the only thing that survives is the C. Instance normalization based is what it says. Based is just a single instance based normalization, so it doesn't collapse over the n. N survives, C survives. Is that only the spatial information collapses. So this is another thing. So instance normalization was used in like a StyleGAN, basically. StyleGAN is before it was, I think it was used for maybe style transfer or some, yeah, I think it was used for style transfer. But then it's it became kind of like an essential core component for actually blowing up this resolution of your image. So if you want to create something like 1024 image, you use something called adaptive instance normalization. Right. Yeah. So that this just a different figure, like what happens with different kinds of normalization. So yeah, I mean, when you're dealing with convolutions, then you are actually dealing with 4D tensors, because there's a batch of different samples, there's different channels, then there's height and width. So it should be a 4D tensor, but we can't draw 4D tensor on 2D plane. So what we do is what happens here is you just merged or concatenated the height and width, the spatial information together, so that we have the 3D tensor. So there's mini batch, there's channel, and there's spatial information. And if you do BatchNorm, what happens is you collapse on two axes, which are BatchNorm axis and the spatial information axis. And the only thing that survives is the channel. So channel survives. If you do layer norm, then the only thing that survives is you collapse everything in the hidden dimensionality. All the hidden dimensionality being the channel and the height and width. So those the hidden representation related information, they are all collapsed, and the only thing that survives is your batch norm. I mean, is your per instance information, basically. And if you do instance normalization, then you don't collapse. You only collapse over spatial information only. So you only collapse over spatial information here, because this is the spatial information axis. So you collapse over here, and then the thing that survives is here. Everything, instances survive and the channels survive. So yeah, it's a different depiction. Yeah, we talked about dropout. Okay, so moving on. Okay, all right. My plan was to talk about the BatchNorm and the CNN architectures in 30 minutes. I guess that won't happen. So I'll only briefly go through ResNet only, and if I have more time after the practice session, then I'll just talk about the VGGNet and Inception net. But in order to do the practice session, we need to learn about ResNet. So in order to do that, I need to talk about ResNet first. Yeah, maybe I'll just take maybe 5 or 10 minutes. So the ResNet is the very first paper that allowed a very super deep convolutions. So we're talking about like 100 layers or even like 1,000 layers. Before ResNet, the maximum number of layers was probably maybe like 15 or 20 or 22 or 25. Even with all the techniques like using ReLUs and all that, yeah, we couldn't go beyond maybe several dozen or a couple dozens. But ResNet was the first one that enabled using hundreds of layers. So this is like a revolutionary paper, a very seminal paper, and it just swept the ImageNet challenge that year. Just it won I think it won every single category of ImageNet challenge. ILSVRC. Not sure what it's short for. Yeah, the basic idea is you just have a residual connection between some layers. So for usually you have a lot of conv plus pool. Sorry, not before pool. There should be. So as I said, the core layers are conv plus nonlinear activation, and maybe pool from time to time. And then you do this a lot of the time. You repeat this conv plus non plus pool again, again and again. So that is the essence of convolutional neural network. And the core idea here in ResNet is the ResNet is short for residual network. And the reason that it's called residual network is let's say that there's an input X here, and what you do is you put you make a highway between here and here like this, or you could do the same. You could put a highway between here and here as well, because as I said, in this guy's perspective, this is the input, right? So like there is always a input between intermediate layers. Like one layer's output is another layer's input. So what you do is you put a residual connection or skip connection between the input and the output of a single, or maybe some nonlinear some nonlinear operations. So let's see. So it could be either you can have, so if you put a skip connection like this, what happens is your new hk equals f w hk minus 1 plus b plus hk minus 1. So that becomes your new hk, right? So what this is the effect of having a residual connection. And the benefit of this is if the extra layers, or if you like having too many layers, the problem with having too many layers is that every single layer needed to learn something, but maybe having too many layers is just unnecessary. Like for example, if you set your model to have 100 layer, but in reality, what you needed to do, the task that you required, the task you wanted to do maybe only required 50 layers. So you just have extra 50 layers lying around, and they don't need to do anything, but you just force the entire thing to learn something. So that is the problem. So if you have some extra layers are laying around and you don't need that layers to do anything, then what necessarily happens is this W can be just a identity matrix, right? If for example, without the skip connection, if without the skip connection, if W H K minus 1 plus B, if without the skip connection, if you don't want to learn anything here, then W must be identity matrix, so that this happen, and of course B needs to be a 0. B needs to be 0. So this needs to be identity matrix, and B needs to be 0. And I mean F is given there, so I mean there's nothing much we can do with F. But what we can do is actually, at least we can learn W to be identity matrix and B to be 0, which is kind of a not an easy task, because you initialize your W using just uniform distribution or normal distribution. So it has it's just like a black and white noise, and trying to force that to become a identity matrix is not an easy job. But if you have a skip connection, then, and you don't want your layer to do anything, then W can be just 0 and B can be 0, which is a way easier job than learning an identity matrix. Learning 0 matrix is way easier than learning identity matrix. So that is the essence of residual connection. By having a residual connection here, this becomes a residual term. So the only thing that the network must learn is the difference between your previous output and your next output. So you just learn the residuals. You don't learn the whole new representation. Your layer needs to learn the residual, and that is why it's called residual network. And the highway or the skip connection can be a bit more adventurous, I would say. So it doesn't necessarily must be like that. It could be you can have a highway like here, or maybe after 3 layers, or maybe after 4 layers. Doesn't matter. It's up to you. Like how many nonlinear operations you want to pack in between a skip connection. That's a designer choice. But it can be as short as just a single nonlinear operation. In the original paper, Residual Network, it was, so yeah, there was a highway, or there was a skip connection between 2 convolutional neural network, two convolutional operations. So there's a skip connection here. And then interestingly, they put the nonlinear activation after the skip connection. I guess that makes sense, because you want to, you don't want to be thrown off by the nonlinear activation value here. So maybe it's a good idea to keep them as a separate thing. But that, again, that's also a tunable factor. It's up to you. So the original architecture is like this. Like there's like a lot of layers. And yeah, so this is the motivation. I'll just skip that. I just talked about the motivation. Why it's a good idea to have the extra term lying around. It's just to it just makes the model, or it just makes the extra layers to learn nothing. Like it just makes the job easy for extra layers to do nothing. Yeah, these are all very elaborate explanation of the why we need to skip connection, but I guess I just talked about that as well again. So yeah, the architecture looks like this. So you start with an input, there's an image, and then you do a initial 7x7 convolutional neural network, 7x7 convolutional operation, and then you do some pooling, and then you start a very repetitive process. So in the first, there are like a lot of blocks here. So there's a block here. I guess it could be like phase one, phase 2, and maybe phase n. And in each phase, the channel grows, the channel size grows. So you can see that this used to be 64 channels, and it becomes 128 channels. And after some phase, some number of another like phases, this becomes finally this becomes 512 channels. And then after that, you pull it and then do a fully connected layer of 1000 output, because you're training your ResNet to do a ImageNet classification. So you need 1000 outputs. So that's it. And the pool here it's called global average pooling. So global average pooling is you just collapse all the channels into a single scalar value. You have 512 channels, right? So you have 512 channels. Like you have 512 of them, and they will be some height and width. You start with a 256, maybe 128 by 128, then this will collapse into some maybe to 128, 120 if you just preserve the dimensionality all the way. But what you do with global average pooling is you just take the mean value of your entire channel. So your entire channel becomes a single scalar value. So this becomes ... So global average pooling is ... You just have 512 dots, and that becomes your so this becomes your 512 dimensional vector, and then you apply a 1000 dimensional linear activation to do the softmax classification. Yeah. So yeah, and the skip connections are made in such a way that you do it after every 2 convolutional operations. So you skip here, and then you skip here, and then you skip here, and then you skip here. Right. Okay, so that's a bit more detail will be given to you in the practice session. Yeah. Well, I mean, I hope that everybody has an idea how to implement this, if they were to implement this from scratch. But of course, there will be some backbone codes given to you in the practice session, and you just need to fill in the gap. But still, if you were to do it from scratch, I hope you have a vaguely rough idea how you would do it, how you would basically you need to repeat this process. You need to repeat this process like several times and several times and several times, right? So you need to code this or implement this in PyTorch, having a convnet, RailU, convnet, and adding a skip connection, then doing a RailU, and then you do a for loop of this for several times. And after several times, you need to jump to phase 2. And when you jump to phase 2, you need to double your channel here. So doubling the channel here. But here, instead of doubling the channel, you do a stride number 2. This is stride value 2. So instead of doubling the channel, you maybe downsize your image, doing the stride 2. And then after that, you repeat this process again, repeat this block several times. And then when you need to jump again, you double your channel, and you set the stride to number 2 again, so that your dimensionality decreases. And then you do this again and again until the very last layer. All right, sorry that I rushed things a little bit. Yeah, there's just a lot of ground to cover, and these are all technical details. And I'm sure you'll run into this anyway when you do the practice session today. So yeah, there are a lot of questions in the chat box. I will address them in the class, and more maybe after the class if there are people still like hanging around. Right. Yeah, there's a lot of good stuff, but it's just that we don't have a lot of time. So we'll just jump right into the practice session today, and then if we have time, we'll talk about a little more material. All right, thank you guys. And TA Hyuntak, please take over. We can start the practice session now.
Okay, can I start now?
Yeah, let me stop sharing my screen.
Yeah. Okay, let me turn on my screen, share my screen. Please wait. Okay, can you see my screen? Okay, thank you. Then I will let me start the practice session. This week we will cover the convolution neural networks, especially the ResNet implementation in this practice session, and especially since we have a time constraint and we don't maybe we can't train the ResNet from scratch on the ImageNet. Then so we will train our ResNet, the small ResNet on the CPR10 dataset, which is given by the distribution dataset in default. So now let me start. First of all, as you can see, the preliminary covers how we import some required libraries and the datasets, and it is very conventional, so you can check easily what libraries are imported. And then we will use the PyTorch convolutional layer, batch normalization layer, and the Drabble layer, and we will construct a simple convolutional neural network to train the MNIST data set. So we also import the MNIST data set and construct the data loaders in this way. If you attended the practice session of the previous lectures, then it is very easy and very comfortable to implementation, right? And today we will since we will implement the ResNet, especially the ResNet 18 to train the CPR10. We also import the CPR10 dataset and construct the data loaders for CPR10 of the train and test splits. And especially different from the MNIST dataset, the data transformation of the CPR10 is a bit complex, but it is very conventional. So it is worth seeing how we will transform our CPR10 data sets to train of training and a test space. So now let me see. The transformation operation of the training data set will be composed of the random like this. The overall message of the transformation of the train is how can we enhance the generalizability of our network to train on the static data set. It means that if our data set can be transformed without losing the semantic meanings of the visual things, then the model also can predict the transformed images in the same way. So the random crop or random horizontal flip means that we will crop the images from the center or the pixel size and flip in the horizontal direction. Then and then in case of human, we will classify the transformed images and original images in the same class then. So we also expect the trained model classify the transformed images and original images in the same class. So we will we will define the transformation of the training data set as like this way. And the test transformation is very simple, and it is very similar to the amnesty data set, except it has additional transformation as a normalization term. And then the training and the train and tested data sets of transformation, the transformation can be injected into the cPattern data set loader, a cPattern data set as in this way. And we will use the 1 to 8 batch size and use 4 workers to define the data loader. Over here, is there any questions? Okay, so let's move on to the next part. From this part, we will cover the convolutional batch normalization and the dropout layer of the in the PyTorch library. So as you can see, the TorchNN package provides the com2d package to define the convolutional layer in demand. So we will in demand, and the signature to use the com2d class is are as like this. So let me explain briefly. The in channel and out channels means that the number of channels of the input images and the output, the number of channels that the outputs of the convolution layer in the with this convolution layer, and the color and stride and padding, which is covered by the lecture. So you can easily see the each meaning of this. So let me try and let me see how to use the convolutional layer in PyTorch and with some example code. So let me define some input images which has 32 by 32 spatial size and 3 channels and also in many cases we use images in a batch manner. So we define the input image X with a 4-dimensional input, which assumes that we have only a single images in a batch. And then, as you can see these images from the lecture note, we will define some convolutional layer that has the 5 by 5 size kernel, and the output channel will be the 1. So the output of the convolutional layer will be sized as 1 by 28 by 28. So in this case, please fill this blank of the convolutional 2D layer of the TorchNN package, and please check the output size of the convolution layer, and it should be matched with a 1/1/20/28. And also check other examples in the lecture note as below. So the in this lecture note, you can also see the other examples in here. So let me see. Yes, the lecture note, page 47. Then you can also check the results of these examples with the PyTorch convolution layer in practice. When you use the input dimension, like, okay, since we assume that there is only a single image in a batch, which is corresponding to the we define the data loader with the batch size as 1, but in many cases we use batch size as 128 or 256. So in these cases, the input dimension, the first argument of the input dimension will be larger than 1. Okay, the next question from the One Hong Yu. In many cases, we don't use the random crop in the test time because we usually want to show our network performance in the same benchmark and the same settings. So we don't use any randomness in the test time. And the next question is from Jawan. Okay, the value in the transforms that normalize is usually not computed by ourselves, but it is shared from other code base. But I don't know in detail, but I will let you know where it comes from after this session. No, as long as I know, the center crop is not the same with the random crop. The center crop, I know when as long as I know the center crop actually different with the random crop. The random horizontal flip is not always required, but in many cases, the human classify the images, the original image and the horizontal flipped images in the same class. So we also expect the neural network classify in a human way. So it is the effort of the generalizability in the trained model. Can I move on to next? Okay. Transform denoise automating quarter. I think I cannot answer these questions in precise and in a proper manner. So I'll let you know, and after this practice session of the question from Jiyun. Yeah. Okay. Okay, so let me see. So you can see the other examples using the PyTorch convolution to the layer with while you fill this blank, and you can easily see the size of the output corresponding to the expected size of the expected size, which is covered by the lecture notes. Okay, let's move on to the batch normalization and the dropout. The batch normalization and the dropout layer is very easy to use, and I think I don't have much talk in this part. So it is very easy to use. The batch normalization. The batch normalization can be imported from the torch.BatchNorm 2D because we will use the convolutional layer and the batch normalization in a sequential manner. So the BatchNorm 2D will be used, and the number of features is corresponding to the output channel of the convolutional layer in usual. And also the dropout 2D also can be used with the probability, which is by default 0.5 value, which is the probability of an element to be zeroed. So it is also helpful to train the model, which is more generalizable, which has more generalizability power in practice. And then after you understand and how to use the batch normalization and the dropout layer with this practice, then you can build a simple convolutional neural network in this practice. So I already specify the input and output channels size and the kernel and the stride size in the comments of the code. And so you can easily fill this blank with And then since we will use this simple convolutional neural network to train the amnesty data set, you can easily know what is the input size, input dimension of the linear layer and output dimension of the linear layer to classify the amnesty data sets in practice. So I will not cover this simple structure, but you can easily check the implemented simple convolutional neural network can be trained on the amnesty with only 20 epochs, and you can easily see the performance on the test data set of the amnesty. So I will move on to the next part of the more popular and the most popular CNN architecture ResNet. In this section, we will implement the ResNet and the effectiveness of the residual connections in terms of the test performance. But because we don't have much time to implement and also trained on the C-pattern data set, we will not cover the whole implementation in this session. And please train your own implemented ResNet on C-pattern after this practice session. And since I already trained the ResNet and the other CNN architectures without the residual connection, so I will show the performance comparison in this section in this section. So the overall structure of the ResNet is like below, but as you can see, some details in the convolution layer or the input and output channel size are a bit different from the residual network covered by the lecture notes because we implement the residual network on the C-pattern data set, which is a much more smaller data set, than the ImageNet. So ImageNet. So we will define and implement a more smaller size residual network in this practice. And so to construct the residual network, we should implement the component of the residual network, which is called the residual block. So the residual block will be implemented to follow this figure. So in a simple manner, let me explain. The input X will be feed forward to the convolutional layer and the intermediate activation function, activation function, and the 3x3 convolutional layer, 3x3 convolution layer will be used, and in some cases, we will use stride size 2 to downsample the input spatial size and the increase the output channels by a factor of 2 in that case. So in the case, and also since the residual network use the residual connection, which simply adding the inputs on the output of the a small convolutional network block. So we will cover this residual block implementation in this part. So I made some blanks in this code, so you can easily fill the blanks in this code with the understanding of the residual connection and the ResNet structure. So you can easily implement it by yourself after this session. And after you fill the blank of this part and run part, then I want to note that simply adding the shortcut, which means the residual connection in this figure, then it won't work. It won't work by default. Okay, the question from Tangjun. Do you mean by the residual connect? Where is the residual connection? Means that in the code or the figure? Can you type code? Okay, the residual connections in the code is implemented in this part and in this part. Okay, sorry. So the residual connection is implemented with a shortcut variable which store the original input X, and the stored original input X will be added to the results of the convolutional blocks, and also as you can see, we will use the residual blocks to construct the ResNet, but in the second and the third residual blocks, the number of output channels will be doubled, and also the spatial size of the input images will be downsampled with a factor of 2. So in this case, the residual connection also downsample the spatial size and also double the channel outputs to connect the residual connections without the dimensional mismatch. So you should implement the downsampling method. You should implement this part to use the downsampling code using the downsample Boolean condition, Boolean conditions in this residual block. I describe and some notes on this text, so you can easily see what should be implemented in this blank and this comment. Let me see the questions from Jaegyun. Okay. No, in short answer, it is not. So the reason why we use the residual is not to train the convolution network, the unnecessary convolution network, but by simply adding the residual connections to the output of the convolutional network, then the network simply use what parameters to be updated while training the whole ResNet architecture. So we simply adding the shortcuts in the output of the convolution network, and yeah, I think the answer will not. I think the answer is not enough to the questions, so I will cover after this practice session. Sorry. Okay. Any other questions with the residual block implementation? Okay, let me explain again about the downsampling. Since the signature and the architecture of the ResNet is using the residual blocks to downsample the spatial size and the doubling the output channels, right? So in this second and the third residual blocks, then we will doubling the channels, and also we will decreasing the spatial size of the inputs with a factor of 2. In this case, the first convolutional layer will use the stride size with the 2 to decrease the spatial size, and also doubling the output channels, right? In this case, the outputs of the convolutional path, the dimension of the outputs of the convolutional path will not match with the original input, right? So in this case, we should downsampling the spatial dimension of the original input, and also doubling the channels to match with the convolutional layer path. So then I can write this. You mean the question from Soro? Do you mean by this code in the ResNet class, right? Or as I explained in this? No. Since the residual blocks will be placed in this. Okay. Let me explain again. Okay, I will I will cover the first question of the Soro first. We will use the n residual blocks, right? The n residual, the output of the n residual blocks will be 16, and output of the n residual blocks will be 32. So this means that the only first residual block of the among the n will decrease the spatial size and doubling the channels, and the other n minus 1 residual blocks will have the same input and output channels, and there is no need to use the downsampling with the n minus 1 residual blocks in this component. And first, combat ResNet, why it has big kernel size as 7 by 7. We do not use the big kernel size as 7 by 7 in this practice session because we will train the ResNet on the CPR10, which is much smaller than the ImageNet dataset size. Okay. The overall, I think it is better to see the overall structure of the residual network, which is use the block as the residual block. So now let me explain the detail of the ResNet class. In the ResNet class, we will firstly use the convolutional, the small convolutional neural networks to make the input with a more increased channel size. So we will use the images, which has RGB channel, three RGB channels, and use a 3 by 3 convolutional layer, and we expect the output of this convolutional block will be 16. So we will now use the 7 by 7 size of the kernel with this CPR10 data set. So okay, and then as I mentioned above, with the overall structure of the ResNet in our case, there are 3 layers which have n residual blocks. So you can so as I mentioned, the first layers with the n residual blocks should output the same size of the output of this first convolutional block. So you can easily fill this blank, and then the other layers with the n residual blocks should output with the downsized spatial dimension and double the size of the output channels. So you can easily fill this blank and destroy the option. So I think the questions from the Soro will be corresponding to the answer of the get layers method in the ResNet class. So the get layers should use the predefined block, which in our case is residual blocks. So we can pass the residual blocks to use the downsample or not with the stride option. And also in the second and the third layer blocks cases, we should downsample the input dimensions and double the output channels. So we only care about the first block of the layer list in this case, and the other n-1 blocks will be used in a very simple manner. So you can implement it here, especially to append and add the blocks with the input channels, output channels, and the stride options to define the each n blocks and add it to the layer list to make a sequential module. The questions from Registral, right? Is downsampling used for each residual block? No. If the layers with the n residual blocks should downsample the image, downsample the input outputs, and double the output channels, then the only first residual block in this layer should use the downsample option. This is the gist of the implementing the residual network. So I recommend you to read the references I attached to the bottom of this practice notes, so you can see the references, and it will be very helpful. Let's try the question from Youngsa. Yes, the stride. Okay, let me show some examples. Let me show the examples in here. Okay. Okay. As we already covered in the lecture note, the 3x3 size filter with a stride 1 option, then and the padding with the 1, then we can keep the input spatial dimension input dimension. So in this case we will use a stride. So it means that if we use the stride 1 with the padding 1 with the 3x3 corner size, then we will keep the input size without downsampling. And if we use the stride size with 2, then it means that we will use the downsampling option, so with the same corner and padding option. You can easily check with some practice with your own Jupyter notebook and simple examples with the convolutional layer definition. Okay, so if you implement the whole residual networks in this manner, then you can easily define the ResNet with various capacity. And in our practice notes, so we will use the ResNet 18, but ResNet 32 is also okay to train the CPR10 data set. And this is the other code that there is to compare the residual network and other CNN architectures without the residual connection options. So we will simply replace the residual block with this block class. Then we can simply define the CNN, simple CNN without the residual connection. So you can easily check the performance comparison with the deeper network size and the effectiveness of the residual connections in this case. So the train code is fully implemented. So you can, so if you implement the Registral, the ResNet class and the Registral block class in a proper manner, then your code will work with this train code. So you can easily check the loss plus and the performance of the simple residual network and the convolutional neural networks without the residual connection. So since the training takes much time, depends on your GPUs or other machine options. So I already trained with this CPR10 dataset and ResNet, and the loss plus will be like this. And if you see the test performance with above the 91 points, then your residual network well implemented. And also, as I mentioned, you can compare the simple plain convolutional neural networks without residual connections on CPR10 datasets. And as you can see, the orange loss line, the orange loss line is above to the loss of the residual network, which means that the residual networks perform better than the other CNN architectures without residual connections. And the questions from Sojung, I mentioned that details in this text, but as let me explain. We usually train the large data sets or large capacity model with the learning rate decay in many cases. So the loss plus of the fall in these time steps this is because we decay the learning rate by a factor of 0.1. So the train with the smaller learning rate might help to converge more better. So the overall practice is this is all about the practice session. So if there is any other questions about the implementation detail or some questions of the use in PyTorch, then please feel free to question in the classroom or mail to me. Thank you for listening.
네, 현탁님 감사합니다. Thank you, TA 현탁, for your detailed explanation and the practice session. Oh yeah, unfortunately we had to rush our material today because we had a lot to cover to begin with. I hope that everybody can go through the codes and actually get familiarized with how ResNet is implemented. I mean, in reality, when you want to use ResNet, you'll just call ResNet as an API because they're already there. Like popular convolutional networks, convolutional models like VGGNet or Inception Block. Yeah, sorry. So popular networks such as VGNet, Inception, or ResNet, they're already implemented in PyTorch. So you can just call them because they're all, the architecture is already there for you. But it's important. I think it's important to know at least how they are implemented, so that if you want to do more in-depth, serious deep learning research or AI research, sometimes you need to actually build things from scratch, and without understanding how these popular models are implemented, there's certain limitation to what you can do. So if you have time, I mean, hopefully you will find time to go through the codes today provided by Hyuntak and actually try to understand what each line and each like segments are doing, so that you can at least have a rough idea how you would implement ResNet from scratch if you were to do so. No, I'm not sharing any screen yet right now. Actually, give me a second. So, but you can't hear my voice, right? Yes. Yeah, I will upload the solution version of the codes on the Classroom. All right. So I'd like to answer some questions that was asked before in the beginning of the class. So, Myung Ji-yoon asked, does BatchNorm occur between input layer and the first hidden layer also? Probably not, because input layer doesn't change. BatchNorm is there because when you update your model, there's an internal distribution shift, but your input, which are the training samples, they don't depend on any learnable parameters. They are fixed values. So there's no reason to use BatchNorm between the input layer and the first hidden layer. Okay. Jaegyun Kim asked, if I don't misremember, last class professor said in these days we don't use BN. Why? Yeah, I guess that was quite a bit of a strong claim. I'm not sure if people use BN explicitly or this. When I read like papers these days, I don't see explicit mention of batch normalization, like whether the authors use batch norm or not. Maybe it's because it's so it's such a given thing. Like, you know, if everybody uses batch norm, then there's no reason to mention that they use batch norm. Or, yeah, I'm not really sure how often they're used. It's not a bad idea to throw them in here and there. But I'm not. But at least the models that I've seen, I don't think they use batch norm that much. Yeah, I'm not sure what the reason is though. I mean, there are different ways to normalize it. Like if you use layer norm, then you don't need to use batch norm. They are kind of two different flavors of normalization. So for example, in transformer or BERT or GPT, like all those, you know, transformer variants, they don't use batch norm, they use layer norm. And I mean, there's a limit there, a bit of a downside of using batch norm is the discrepancy between the training time and test time, as I said. So it's probably better to not have the discrepancy by using layer norm instead of batch norm, and you can still achieve similar, like, you know, normalization effect. They won't be the same. Like layer norm and batch norm are not the same thing, and sometimes, or maybe most times, batch norm are more efficient than layer norms. But it's just that it's easier to use. Like there's one less thing to care about. If you use batch norm, you need to care about the running average and then saving them and then reusing it in test time. If you use layer norm, you don't have to think about that. This just makes your life easier. So that's that. Pegumi asked, why do you keep certain dimension, keep certain axes around? Like why do you make them survive? Like such as C and N, a C or the channel, or N being the batch axis. Yeah, it's as you said. There's a specific reason why they do so. So batch norm is, as the name says, you normalize across the batch. So you collapse, or you gather the statistics across the batch axis, the N axis. So the C survives. If you do layer norm, then what you want to do is you don't want to be you don't want to be affected by the size of your batch, mini batch. So you don't want to collect your statistics across the batch axis. You want to collect the statistics, the mu's and standard, the mu's and sigma. You want to collect their values across the hidden dimensions. That's why the n-axis survives in that case. And if you do instance normalization, then like another combination of axes survives. So yeah, they serve different purposes. All right, so I think I answered all the questions so far, either using text in chat box or just verbally. How many people do we have around? We have 70-ish people. So let's see. Are you? So 70 people here. Are you guys here so that I could explain like the popular architectures, the VGGNet and Inception net that I just skipped over, or is there any reason that you're like sticking around? Or do you? No, not actually. Or do you have any questions or? Let me just take a poll. Like who would you like me to go through the popular architectures, the VGNet and Inception net? Okay, at least there's one person. All right, okay, we can do that. Yeah, before I start with the VGNet, maybe I can just give a little more detailed explanation on ResNet, like why they're such an awesome architecture. Okay, so all right, no question. All right, moving on. So the reason that yeah, it's a very keen observation by the authors of ResNet that what used to happen before ResNet is that, like for example, if you increase the number of layers, or that means you're increasing the power of your model, because more layers means more parameters, more nonlinear operations, and more power to the model. But it didn't work. It didn't even overfit. So the problem with the so there's training error, and then there's test error. And if the model was overfitting, that means the more powerful model would have lower training error but higher test error. But that's not the case here. It is the case that the smaller layer, the model with the weaker expressibility, or the less powerful model achieves smaller training error, means like better better accuracy, right? So weaker model is doing better job than stronger model in both training error and test error, which means that the stronger model, or the deeper model, is not overfitting. There's something wrong with the optimization. So it's yeah, not caused by overfitting. It's not the overfitting. It's the optimization problem. Something is wrong. We're not just optimizing the model appropriately. So we haven't even got to the point where powerful model overfits. We haven't even seen overfitting yet. It's just we can't just handle how the bigger model to get lower training error. So the problem lies with the optimization, not the overfitting. So that's why the authors of ResNet came up with the residual network, to make the optimization process easier for deeper models, right? Yeah, it's just exactly like this. So if you have one more component layer, or if you just start adding more layers and more layers, but if they happen to be identity layers, then you might as well just don't have that layers, right? So it's the same principle. If you just have a lot of layers that can learn to do nothing means just identity mapping. You just carry what is given to you to the next layer. So it's a carryover layer. And if your multiple layers can learn to carry over simply, then there's no like there's no downside of having a lot of layers, because if you have too many layers, then they'll just learn to do nothing, right? So that is the whole idea of residual connection. So yeah, identity mapping is allowed by having a skip connection, and then your network can learn to do nothing way easier than before, because these just needs to be 0 instead of your yeah, without the skip connection here, without the skip connection, if you want to carry over, if your layer needs to learn to carry over, then the whole thing must be the same as X, right? But if there's a skip connection and you want to carry over, then your internal, your learnable parameters or your operation needs to learn to be 0, which is way easier than just learning to be X, your input. So that's the whole, like, theory behind why residual connection is such a great model. Right. Yeah. So so theoretically, yes, your residual layer, your fx, which is intermediate, the non-linear operation between the skip connection, needs to learn the residual being the difference between this and this here. The only, yeah, it is just learning the like the error, so to speak. Yep. Yeah, I hope this makes the theory or the motivation behind ResNet more clear. All right, some questions. I still have a question about ResNet. I do not understand why we skip the layers if we're not using them. Why do we keep? In case we need them. So we don't know. Like we don't know the ideal number of layers to use. Like, because what is the ideal number of layers to use for ImageNet classification? Is it 250 or is it 125 or is it 64 or is it maybe it's 5,000? We don't know. So, but we would like to use a lot of layers just in case, just to be on the safe side. And as long as they can learn to do nothing, then we're not losing anything. 맞습니다, 박영선님. 네, 딱 그 말씀이에요. It's just learning the difference between input and output. Yeah. Right. So yes, I think I answered Andre's question. And 최상범님, to maintain the signal strength of error backpropagation. I guess you could say that, but it's maintaining the signal strength of error is, I guess, that more pertains to batch normalization rather than ResNet. ResNet is just making the job of each layers easier because you're just learning the difference between input and output. Okay, yeah, I hope that's clear. Yeah, they're just a bunch of details. So as I said, there's a repeated component or like residual blocks that you use in each, like every, like here and here and here. And as I said, you double after each phase, you double the channel with stride 2, spatially with stride 2. And next one is, yeah, so the full architecture is stack of residual blocks, stack. The residual block being this guy. You stack them like 1, 2, 3, 4, 5, 6, like a lot of them. And then there's like a phase here, like phase 1, phase 2, phase n. And periodically means different phases. Periodically, when you jump from one phase to another, you double the number of channels or double number of filters, and downsample by using stride 2. That's it. Right. And finally, there's, yeah, I briefly talked about the sequence of fully connected layers after the convolutional layers that used to be there in the AlexNet or VGGNet, and that's not there anymore. There's no fully connected layers, like sequence of FC layers. There's just global average pooling. As I said, there's global average pooling here, and then you just have one linear, a fully connected layer to predict the class of your images. So it's image classification. So you need 1,000 classes. So that's all there is. Just one FC layer. That's it. Yep, and yeah, depending on how many blocks you use, how many phases there are different layers. Like you can have ResNet 18, ResNet 34, ResNet 50, 100, 152. I think people use ResNet 50 a lot as like a, you know, like a backbone structure. If you need to do anything with an image, like if you want to do image captioning or style transfer or object detection or segment or pixel segmentation, whatever. If you want to do whatever, usually people use ResNet 50. And yeah, this is the training details. Like you still use BatchNorm here inside the ResNet, and there's something called Xavier Initialization. It's like initializing technique, like how you want to initialize the weight parameters, the weight matrices. You use stochastic gradient descent with momentum. This is also another like optimization trick. There's a lot of trick going on basically. Interestingly, no dropout is used. So it's just you just have the Bachelor Normalization and ResNet, and no dropout. Yeah, and it just swept the first place, all the challenges in 2015 ILS, VRC, and COCO competitions. So it's first place, like all first place, and the gap between the first place and the second place was pretty big. So it was a very yeah, it's a very phenomenal paper. Yeah, before we move on to that, let's just go back all the way to the VGGNet and InceptionNet. Some questions. Okay. 배울 것이 없을 때 F는 영어를 만들게 되면 모듈 레어 리지컬 컬렉션 리지컬 이겨도 이성준님이 질문을 하시다 만 것 같은데 무슨 뜻인지 모르겠네요. 네, 모든 레어 리지컬 커넥션을 둬도 상관없습니다. 어쨌든 그것은 다 예. It's up to you how many layers you want to skip by making a residual connection. If you want to skip 2 layers or 3 layers, it's all up to you. Yeah, it's a designer's choice. It's a hyperparameter. It just so happens that the original authors just skipped 2 layers, but there's no reason you can skip 3 layers or just 1 layer. It's up to you. Rushda, during backpropagation, it transcends through the skip layer as well. Of course. Now, transcends, I'm not sure what you mean by transcends, but it's just, you know, the error signal is propagated through the skip connection as well, because you're adding your input to the output. So the add addition, that plus sign, that is making a connection. So the error signals go through that connection as well. 박영선님 질문. Some guy named user. 스킵 커넥션 사이의 네트워크는 영에다 학습하는 겁니다. 일부 노드를 주세요. 네, 맞습니다. 뭐 그렇다고 볼 수도 있는데요. 보통은 그렇게 한 레이어 전체가, 그러니까 스킵 커넥션을 한다 그래가지고 그 FX가 빵이 되는 경우는 별로 없습니다. 다 뭔가를 배우긴 배워요. 그러니까 드롭아웃처럼 이제 아주 그 극단적으로 빵이 되는 효과까지는 아닌데 뭐 그렇다고 볼 수도 있습니다. 네. 박영선님, 아이덴티 매핑을 하면 왜 옵티마이제이션 프로블럼이 해결되는 건가요? 그러니까 네. 예를 들어서 1000개짜리 레이어를 쓴다 그러면은 1000개를 일일이 다 학습을 해줘야 되는데, 이게 만약에 1000개 중에 999개가 아이덴티 매핑이면은 그럼 하나만 학습해도 되는 효과가 있잖아요. 그런 식으로 보시면 됩니다. 극단적으로 보자면 그렇게 됩니다. 그러니까 준비는 1000개를 해놓되 각 레이어가 언제든지 아이덴티티 매핑을 배울 수 있도록 세팅을 잘 해주면은 이게 필요에 따라서 몇 개를 쓰는지 알아서 결정이 될 거잖아요. 1000개를 다 써도 되고 500개만 써도 되고 1개만 써도 되고, 푸는 문제가 쉬우면 하나만 쓸 테고 푸는 문제가 어려우면 1000개를 다 쓸 테고. 근데 이제 각각이 아이덴티티 매핑을 배우기 쉬운 상태로 지금 스킵 커넥션을 이용해서 이게 마사지를 해놨기 때문에 이제 이게 옵티마이제이션이 쉬워진다 이겁니다. From Danielle, would you please explain why some people do flattening before dropout and then they dense the link? I'm not sure if I understand your question. What do you mean by flattening before dropout? Like, do you mean the spatial information, the height and width in your hidden convolute in your hidden layer? Yeah, I'm not really sure what you mean. Like, I haven't. Yeah, at least I haven't covered that in the lecture. Assuming that people, this is all assumption. This is all just out of my head. Assuming that when people want to use dropout in convnets, they want to do it in such a way they just destroy the spatial information, flatten your hidden layer. So because in convnet, in convnet, when there's multiple layers of convolutional networks, the hidden feature between the layers, they look like a 4D tensor. So I'm just gonna draw it in a 3D manner. So this is your batch norm, and this is your batch axis. So different samples. This is your channel, and this is your no. I'm sorry. So what do we have? Yeah, this is your height and width, and maybe some people want to collapse this into this looking like this, like just B here, and no, actually no, B times. I'm sorry, not B. I'm sorry, not this. Not this. It should look like this. So B here, the B survives, and then there's just one long horizontal axis, C times H times W, and then you do dropout on top of this. And maybe that's what some people do. I'm not sure if that's a common technique though. All right, moving on to, yeah, so it's already, what time is it now? It's 12:20. All right, let's just try to wrap it up in 20 minutes, maybe. All right, so yeah, so this is the history of ImageNet challenge, and prior to 2012, which is the birth of deep learning. This was all like shallow days, I guess, non deep learning era, and then so two things, maybe three things, yeah, four notable things I would say. So there's AlexNet, and there's VGGNet, and then there's InceptionNet, and then there's ResNet, and after that it's just more or less just fine tuning and more engineering. By the way, human performance is 95% accuracy. So ResNet is already superhuman. ZFNet, Zeiler and Fergusnet, this is also mentioned from time to time, but most notable popular networks are AlexNet, VGNet, InceptionNet, and ResNet. And AlexNet is a pretty complicated architecture with a lot of learnable parameters. This is like the largest model number parameter wise, but it just performs worse than the more efficient ones. The ones that come later, like 2014, like VGNet, InceptionNet, ResNet, they use less number of parameters compared to AlexNet, but they achieve way better performance. So it's just better architecture, basically. So yeah, nothing too much to talk about AlexNet. It's just complicated. There's just like two streams here. You have an input image, and then there's one stream that's going this way, and another stream going this way, and then you just mix and match with a fully connected net, fully connected layers at the top. Yeah, first use of ReLU, and there was a dropout already used before the dropout paper was published. So it's a pretty pioneering paper. We'll move on to VGGNet directly. So VGGNet is deeper than AlexNet. AlexNet used 8 layers. VGGNet used VGG16. This is like the popular one. VGG16 used 16 layers. And instead of using like big convolutional big con filters, like 11 by 11, AlexNet uses 11 by 11 filter, which is like gigantic by today's standards. And then there's 5 by 5. But if you look at VGG, it's all 3 by 3. It's all 3 by 3, 3 by 3, 3 by 3, 3 by 3. And as I said, if you stack up multiple layers of 3 by 3, it's the equivalent effect of having a single large filter, and you still use less number of parameters. You use less number of parameters, and you do multiple. You just use one more number of nonlinear operations. So it's just better to use, sequence of small filters rather than just one gigantic filter. So that's what VGGNet actually did. So it's a pretty pretty standard practice. You have 2 confidence, 1 pull, 2 confident, 1 pull, 2 confident, 1 pull, 3 confident, 1 pull, 3 confident, 1 pull, and then just sequence of fully connected nets. So it's a pretty standard standard operation. And there's another variation called VGG19, which uses a bit more layers. So there's instead of 3 and 3, you use 4 and 4. That's it. Yeah. There's less number of tricky engineering things that was used in AlexNet, and it's a simpler architecture, less number of parameters, deeper layers, and better performance. So all in all, just a good architecture. And then after that comes GoogleNet or Inception Net. So it's called Inception Net because this is the first time, I guess it could be said this is the first time they use a repetition of a block. Like in ResNet, you repeatedly use residual block, like multiple times. Here you have something called inception module. And you repeatedly use this in multiple places. Of course, I mean, just like in ResNet, even if you use multiple blocks of residual blocks, it doesn't mean their weights or learnable parameters are tied. They're different. They have different, like, let me just jump to ResNet. Yeah, just right here. Even if you use the same block all the time, like here, it doesn't mean you're recycling the block. It doesn't mean that you use the same weight parameters over and over and over again. It's just that the architecture is the same. The weights are different. So this whole thing, like here, one using in here and here and here, they are differently initialized with different learnable weight parameters. They're not the same thing. Okay, it's just that the architecture is the same. The shape, the structure is the same. Their weights are different. And in the same sense, even before that, Inception that came up with that idea before that. So they have something called Inception Block or Inception Module, and you reuse this. If you look at the entire Inception network, you reuse this here, here. Like you just stack these up all the way till the end. And they just have the same architecture, but they still have different weight parameters. So it's a pretty deep network compared to VGGNet. It uses 22 layers and only 5 million parameters, which is 12 times less than AlexNet, 27 times less than VGG16. So it's a very efficient, model. And of course, there's no FC layer. So if you look at this at the top, there's let me see. Yeah, I think there's only one global average pulling here. One global average pulling, then you need the final FC layer for predicting your image class. So that's all there is to it. Yeah. So yeah, okay. So that is why it's called Inception. That you have a Inception module that is used all over the place, and it's the same principle applies to Inception version 1, Inception version 2, Inception version 3, Inception version 4. It's all the same. It's just that the architecture is like slightly different from one to another. So yeah. Yeah, they're inside the entire network, so it's Inception module, just like the movie Inception, I guess. Yeah, just similar to the ResNet, you start with some initial convolutional operations. In this case, they used the resolution is not good enough. In ResNet, they started with 7x7 confidence with stride 2. I think they used some preliminary, seed operations, or they call it STEM network. Some seed operations or initial operations that you massage your input to make it into a smaller feature size, and then you start repeating the Inception modules over and over again. So yeah, they are the stacked Inception modules. And then there's the final classifier output, and you can see that the same classifier output is added, like slid in, like thrown in from time to time between the layers. It's just to give the error message more efficiently. Like if you think about, if there was no such thing as this block and this block here, then the entire network must depend on the error signals coming from this final classification error or cross entropy error. But if you slide in the same architecture here and here, then the same kind of signal flows from here as well, and here as well, and here as well. So you get more signals basically. It's just for, so it's a trick, kind of a trick to add in like intermediate output classification error signal from time to time. Yeah. Yeah, I already talked about global average polling. This is just, you take the entire, you collapse the entire spatial information into a single scalar value. So H and W becomes 1 and 1. You just collapse your entire channel into a scalar value. And if you have like 100 channels, then you're left with 100 scalar, which is just a vector, like 100 dimensional vector. Yeah, and this is auxiliary classification outputs to inject additional gradient at lower layers. Yep. Yeah, this is just saying like how you calculate the total number of layers. There's like the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, something like this. You calculate the number of layers. The important thing is how they constructed the Inception module. Actually, they wanted to make it into an efficient network. It uses only 5 million parameter, which is like 27 times less than VGGNet, as I said. So the important thing is how they constructed the Inception module to make it into to repeatedly use this to make an efficient entire model, right? So the way they did it is they used heavily depended on one-by-one convolution, actually. So one-by-one convolution is used everywhere. There's one-by-one convolution here. And I hope you guys remember, one-by-one convolution is basically contracting the channel size. For example, if this is your, I'm gonna throw away the batch axis. So we're only talking about a single image. So there's H and there's W, and then there's channel, right? And the 1D1 convolution is applied. So the 3x3 convolution is applied like this, like 3 by 3. If you do 1x1 convolution, that is only applied to a single pixel in like a fiber-like manner, like here. And then if you use 1x1 convolution filter with maybe, let's say this was 64, and you use 1x1 convolution filter with channel size 32, then what happens is you retain the dimensional, you retain the spatial information. It's just that your channel is halved like this. Your C becomes 32 with 1x1 conv with 32 channels. Then you're left with 32 channels only, while retaining H and W spatial information. So basically, 1x1 convolution is like a channel contraction or channel compression algorithm. So by compressing your channel a lot of the time, you are left with way smaller feature size, and then that's how you make a efficient Inception module. So there's basically 4 different channels. Oh, actually, yeah, this is okay. This is a last slide. Okay, that's good. Let me just explain it in a little more detail. So given a previous layer's output, so previous layer's activation, which would be a 4D tensor. So there's like 4D tensor being this going to be your batch axis. This is going to be your channel axis. This is going to be your H and W axis. So your module is given this, and a single Inception module, there are 4 streams basically. There's a straight 1x1 convolution. And then which is retaining the which is retaining. Actually, let me erase the batch axis here. It's better to explain with C, H, and W. H, W, and C. So you're given this, and then if the first stream or first channel, not channel is not a channel, it could be ambiguous. So first stream retains H and W, like this. So it is still H and W. It's just that your channel probably has decreased into some smaller channel, C prime, because you're doing 1x1 convolution. Another stream is using 3x3 convolution, so there will be some different. It'll be a little bit contracted because I'm not sure, I don't think they use padding here. Did they use padding? I don't think they use padding here. So another C prime and H prime and W prime because you're using 3x3 con filter with 1x1 convolution. So there's C prime, H prime, W prime. 5x5. This is going to be even more smaller than the 3x3 convolution with another C prime. So C prime, H double prime, W double prime. And another stream is what? It's a 3x3 max pooling. So you do max pooling like this. So 3x3 max pooling. So you're contracting your spatial feature into a third, like 33% survives. So this becomes even more, like way smaller than before as well. So this is like H triple prime, W triple prime, and C prime. So you have a lot of streams. You have like a stream that retains the spatial information, stream that does 3x3 comp, stream that does 5x5 comp, stream that does max pooling, and then after you obtain the output from different streams, you concatenate them. So you just put everything together into a very like one gigantic, like some hidden feature or hidden tensor that is like gigantically long like this, because you want to concatenate them, and then you do some massage to even contract them again into like even smaller feature size. So that's how you do a efficient operation on a huge tensors. Basically, you heavily use the 1x1 convolution a lot of times, so that the channel axis is massively compressed, and then you do a 3x3, 5x5 convolution on top of that, and then you return it to the original feature size or channel size. So you do this again and again, like repeat it here, a lot of times, and then that's how you retain the feature size while doing a lot of like convolutional operations. So that's where the efficiency of Inception comes from. C 프라임은 동일한 건가요? 저도 사실 모르겠습니다. 저도 뭐 코드를 본 건 아닌데, 그러니까 여기서 1x1 컨브가 몇 채널을 사용했는지에 따라 다 다르겠죠. 여기서 1x1 컨브가 뭐 24채널 사용하고, 여기서 뭐 32채널 사용하고, 여기서 뭐 48채널 사용하고 그랬을 수도 있거든요. 그러면 당연히 여기 C 프라임하고 여기 C 프라임, 여기 C 프라임 다 다를 텐데, 뭐 아마도 똑같은 채널을 사용하지 않았을까 생각을 합니다. 아마 뭐 기존에 있던 C가 뭐 예를 들어서 512였으면은 이걸 전부 다, 이건 채널이 지금 4개, 스트림이 4개가 있으니까 다 4분의 1로 줄여가지고, 뭐 이게 4분의 1 몇이죠? 뭐 128이죠. 이제 여기서 여기 C 프라임이 128, 여기 C 프라임도 128, 여기도 128, 여기도 128 해서 다시 다 컨캣하면 또 원래 512로 돌아가잖아요. 아마 뭐 그렇게 하지 않았을까 생각합니다. 중간중간 빠져나온 것은 백프랍에 활용되는 예인데, 요 중간중간 빠져나온 것들은 백프랍에 활용되는 겁니다. 최종 클래시파이어와 인터미디어 클래시파이어 구성은 같나요? 그거는 생긴 건 똑같아 보이는데 아마 조금 다른 것 같네요. 조금 다르네. 여기서 이제 FC가 하나인데 여기서 FC가 2개 있는 거 보면 뭐 조금 다른 것 같긴 합니다. 아마 중간에 넣어주면은 그만큼 이제 많이 이렇게 레이어를 통과시켜가지고 마사지를 많이 한 것보다는 아무래도 파워가 떨어지니까 중간에 일부러 이렇게 FC 레이어를 2개 정도 넣어준 것 같아요. 마지막에 하나인 것보다는. 근데 아마 근데 이제 여기 소프트맥스랑 뭐 이런 풀링이랑 이건 똑같이 구성이 될 겁니다. Okay, so we just have one final interesting figure here. So, right. So yeah, this is the best. Okay, so this is the best accuracy so far. So AlexNet accuracy is pretty poor. Top 1 accuracy. So like you're doing ImageNet classification. So a single image, for a single given image, you can have like multiple predictions. Like it could be a dog or a cat or whatever, and you just top one accuracy means you just take top 1 strongest class from your softmax output, and if that's correct, then it is accurate. So that's top 1 accuracy. And ResNet top 1 accuracy is below 55%. ResNet 18 is about 70%. ResNet 152 is about 70, I would say 7-ish, 77. Inception v4, the most recent Inception net is 80%. And then there's like an interesting diagram between the comparison between accuracy and the number of operations, or base number of operations, or maybe the size of the neural network, which is correlated. So VGGNet is the biggest one. VG19. I guess I may have misinterpreted. I said AlexNet is the biggest one, but that is not true. So it's the VGGNet is the largest one. It has the largest number of parameters and the largest number of operations required. Compared to that, the accuracy is not that impressive. So it's somewhere in the 70s, right? Compared to that, Inception v4 here has a way less number of operations and way less number of parameters. It's only 35 million, and it is showing the highest top one accuracy. So there's still like a lot of rooms to meddle with the structure of your network. Just because there's ResNet, and then just because there's like a ResNet 152, it doesn't mean all the problems are solved. You can still do a lot of interesting stuff. You can try to compress your model, like downsize your model, and still retain the accuracy. Or maybe you can go deeper. You can go make it more efficient, or maybe just try to achieve higher accuracy. There's a lot of different ways you can research. And yeah, I think this is a very interesting figure. All right, so I think exactly 20 minutes, exactly 20 more minutes I took. All right. Okay, so I still think we've rushed a bit, but I hope that at least everybody understands roughly what I wanted to tell, what I wanted to convey. So thank you very much. Are there any questions so far? 이재원님, 네, 그럼 다 모두 그러니까 이제 다 비슷해지겠죠. 어느 정도 다 이제 센터 노멀라이즈 돼 있을 텐데, 이제 그 아까 보여드렸듯이 감마랑 베타 러너블 파라미터가 있기 때문에 모든 레이어가 다 비슷해지진 않을 거예요. 다 이제 어느 정도의 그 자유도는 있지만 너무 이제 아주 다르진 않다. 그러니까 레이어마다의 그 디스트리뷰션이 아주 막 천차만별은 아닐 것이다. 네, 어느 정도 어쨌든 다 이제 유닛 노멀라이즈 됐을 거기 때문에 그 정도로 봐주시면 될 것 같습니다. 네, 그 정도만 해도 레이어마다 천차만별로 다른 것보다 훨씬 학습이 쉽다는 거가 이제 배치놈의 어떤 정신이라고 볼 수 있습니다. Yeah, any more question? 네, 뭐 질문 없으시면은 이제 그래도 끝까지 40분이나 남아주셨네요. 네, 감사합니다. 그러면은 다음 주는 이제 다음 주는 그 중간고사니까. Okay, so the next week is midterm week, so we will just we'll meet again the week after that. So good luck with your midterms and good luck with your projects. I mean, honestly, they're not that difficult. So yeah, just take your time and just try to train it as sufficiently as possible, and you'll be fine. 네, 다음 주 수업 없습니다. So no class next week. So you can just focus on your midterms for other classes. So no class next week. It is just midterm week. We'll resume week after that. All right, thank you guys. If you have any questions, please post them on Classroom. See you the week after next week. Bye-bye.